Welcome to my public PhD defense and thanks for coming. So I will present you the work that deals with the optimal design applied to solar-assisted hydrothermal gasification plants. So I will introduce a bit the problem, then I will show what are the main two methods that I have developed to design a solar-assisted gasification plant. In particular, I will look at the first of three design methods. So this, for those that are not familiar with this topic, is a let's say preliminary analysis that it is necessary to introduce and to see what are the options when designing a power and a chemical plant. In this topic, we will see what is utility expression. Then I will describe the framework that I have developed, and I will show the application to the solar-assisted hydrothermal gasification. Then we will go a bit more in detail, and I will present the method that I have developed for the design. So in this case, we will obtain a more detailed view of the energy and chemical plant. In particular, we will have a look at the framework for the sequential synthesis of heat exchanger networks they have developed and published. We will see that I made some comparisons of these two case studies in order to see where I was, and then we'll see the extension of this method to optimization. Finally, I will show the application of one of these methods, the solar-assisted hydrothermal gasification, some conclusions. So in order to introduce the the topic, why this topic? If you look at this blue map scenario that is provided by the International Energy Agency, we see that the use of renewable energies may allow to reduce the carbon dioxide emission for for almost 17%. In this group of renewable energies, we have biomass, we have waste biomass, we have waste wet biomass, and we have solar energy. When I say waste wet biomass, I define it as biomass with a solid content less than 20%. Then, if we look in particular waste wet biomass, in the case of Switzerland, we see that there is a potential of converting into energy, so electricity and available heat, almost 7.5% of the Swiss primary energy consumption. This is the unused biomass. If we consider the wet biomass, we are about 4% of the Swiss primary energy consumption. So in my thesis, the idea was to have a look in particular at energy conversion technologies that are able to convert this feedstock to fuels, electricity, gas, and heat, and to include solar energy to the design. In particular, I was looking at hydrothermal gasification. What is hydrothermal gasification? It's a quite new way of converting wet biomass. One of the main advantages is that we do not only convert biomass, but we can also recover nutrients. And we have a kind of pre-treatment plant for water. We have a feedstock that has a high water content. We have also multiple products. So if we have a look at the simplified process flow technology, we see that we start from this waste biomass, which is a slurry. Here it is represented in brown, so you can imagine what this slurry is. Then we can pump it and heat it up, and by performing a thermochemical conversion, it is possible to separate the salts because we are going into supercritical condition, and in this condition, the salt crystallization is particular. And then, having separated the salts, we are able to have a gasification, so to convert part of the organic that is inside the biomass into fuel. So, at this point is a mass flow, which is rich in methane and water. We have also some byproducts like CO and CO2 that we need to remove in order to, and water, in order to match the quality of the grid gas. we are supposed to sell this. So my thesis, I was looking at this particular technology, which is in fact studied also at the Polcher Institute, where Professor Vogel has developed this experimental setup and has proved that this conversion is possible in the range of. Why I choose this? There are also other type of gasification, but I choose in particular this type for three main reasons. First of all, this type of gasification has a heat demand which is at relatively low temperature, which means that basically so if we do the energy balance, considering this control volume, we see that we have to provide some external energy in order to satisfy the process requirements. In this case, the requirements are at low temperature, are relatively low temperature. We talk about heat at 380, 400 degrees. So this was the first reason. Second reason was that the gas product is a methane-rich gas. So we have the ability to develop a technology that produces a ready-to-use fuel, for which the infrastructure for transport, storing, and using this fuel is well developed. And one of the, let's say, problems related to this technology is that we have to, of course, separate water and CO2 that are present at the end of this gasification. For this reason, I developed a second model, which consider a modified version of this hydrogen in order to convert part of the CO2 into called the Sabatier reaction. It is a reaction that will happen inside this catalytic. So, thanks to my computer simulation, I was able to calculate this process flow sheet diagram and to calculate the composition at the reactor output. What is the advantage? That by adding hydrogen, it's possible to theoretically remove the CO2 from the gas product and increase the methane. So here the question was if it's better to invest into hydrogen technology in order to not have a CO2 capture technology at the bottom of our plant, or is it better to keep the let's say more the conventional way of producing a gas and then removing. Then comes the problem of the gas separation options. As we can see, there are several ways of separating this gas, so removing the CO2. We could use selective absorption, water absorption, and every time we consider these separate systems, we have to include into the energy balance heat and electricity. So in this case, the problem becomes quite tricky because streams have a cost which is associated to them, and we would like always to have the perfect separation process would be the one with very high efficiency. So we are able to separate all the CO2. We are able to buy this system very cheap. It's running almost for free, and we can eventually even convert power and so in this case, there is a need of simultaneous evaluation of multiple criteria. We have the energy aspect, the environmental aspect, and the economic. So looking at the gasification process and the gas separation process, the problem is that, as I was saying, the energy balance is not closed. So we need to provide from external, from another source, heat to heat up this process. There are mainly three ways of doing this. It would be possible to use normally. It would be possible to use part of the fuel in order to to satisfy the remaining requirement. Alternatively, it would be possible to convert fuel and gases into heat detected in our system, but of course, combustion, they will reduce the waste to fuel conversion. So in this context, solar energy can play an important role because we should remove we should substitute this fuel, this amount of fuel with this amount of solar energy, and this would allow to increase the waste to fuel efficiency. What are the benefits? Benefits are that solar energy is an almost free added energy. I mean, that once we have installed our plant, the operation will be cost, but the sun will be for free. The radiation is still a free source of energy. We will have an increased waste to energy conversion, and this system would represent also an option to store solar energy into fuel. But as far as we include this option, the problem gets more complicated for the reason that sun is not a steady state utility, so it's not something that is there all hours of the year. And this reason we will have to consider a multi-period optimization. So we have to consider the time. So then solar energy in general, but solar energy can be converted into heat, electricity, or hydrogen, and there are a multitude of technologies to do this conversion. In the pre-design phase, we will see that I focus my attention on the most promising sun to fuel, sun to electricity, and sun to heat technologies, and I try to define a method to get oriented when we have to select among a set of possibilities. So in this thesis, to end up the introduction, the methodologies I have developed, they deal with several topics. First of all, we have a thermoeconomic modeling, which is basically linked with the representation of a physical system into mathematical equations, using mathematical equations, taking into account economics and thermodynamics. Second topic is the print analysis and process integration, which is a theory that allows to try to maximize the efficiency of a system by maximizing the recovery of unused energy. And then I deal with uncertainty analysis. In this case, the goal is to see what is the impact of considering uncertain parameters into a simulation and optimization model, and how this can affect the model output. Then, for the design phase, heat exchanger network design was tackled. In this case, we see a representation of industrial plant in which you have a lot of hot and cold thermal streams that have to be done and heated up in different periods with different target temperatures and different target heat loads. And finally, all these aspects have been included using optimization techniques, where the goal is to find the optimum of a given function. And here we see that I represent a subspace, which is a function of two variables. And just to give you an idea of optimization, the exploration of this space and the identification of points where the objective function, which is here represented, or maximum, depending on the. So, at the end of this introduction, there are three main research questions. The first one deals with the definition of a method for the identification of most promising energy conversion paths. This is a pre-design analysis that is also known as targeting analysis. In this case, I wanted to take into account uncertainties and to evaluate and to select most promising energy conversion paths. Second research objective is linked with the definition, development of design methodology that would allow to optimize utility integration, scheduling, and heat exchanger network, considering uh, plants and chemical power plants and chemical plants where multi-period operations are needed. And finally, as third research objective, I wanted to apply the considered methodology to the solar-assisted catalytic hydrothermal gasification system. So this is a way to prove that the validity of this method and to show if some novelties are coming out. So let's start with the pre-design analysis. In this case, I will introduce a bit the problem. So the problem is that we have given a set of energy conversion technologies, P and U, where P are the process units, process units, because they are fixed in size. And U are the utility units, where U are the units that can be varied in size. We have a superstructure where these units are linked, and so these links represent material and energy flows. These units have to have some performance parameters and have some economic performance parameters. And so given this, every unit is it's not that it exists, but our goal is to see which units have to be activated in this chain. So in this context, we have to determine what are the utilities that are to be purchased, and we will use a variable 01 to determine which ones have to be selected. And then once we have decided which ones have to be selected, the problem is also let's determine their size, their operation during the year, by associating a continuous variable. So this is the starting structure, and I have highlighted in blue the utilities that have been selected. So here we have an example of three solutions. See that process is always selected because by definition it's existing. Then this could be an option in which we have activated this could be another option, and this could be a third option. Each of these, I will then show you what are these units in practice. So, how to solve this problem? The classical approach to solve this problem is to consider some input parameters. Was the approach proposed by Palazzi in 2007. The approach is the following. So, given the input parameters, we can first simulate the flow sheet. So, the models of the physical systems we had, they can be simulated on the board. After this, the energy integration is an optimization technique that will allow to optimize the energy and mass integration in order to select the utilities U that I showed before that have to be included in the solution. Once we have, so this is a key step that will decide among a set of several energy conversion units, such as solar concentration technologies, storage options, etc., which one is the one that will be it should be installed. And then, given this, we should also we can also calculate some economic and energy efficiency performances in a post calculation. When I started my PhD, this was the approach that was used, and I asked myself, so what happens if the inputs of this model are uncertain? How the solution will be affected by this uncertainty? So for this reason, I developed a framework in order that is a B-level framework, so a framework that allows to have a look at all the possible solutions and get oriented inside this in this solution space. The first upper level, so it's a B-level approach because we have an upper level step, a second upper level step, And then we have a lower level step, which is the same approach that I have presented before. So given the set of uncertain parameters, I first apply a global sensitivity analysis method with the goal to identify the influential uncertain parameters, because often we have a lot of parameters that we consider as uncertain, but in reality, with respect of our goal, so with respect of our solution, the U want, these uncertain, some of few of these uncertain parameters are really affecting the solution. So this first method allows to start from a certain number of parameters and reduce the number of parameters. At the second level, at the second upper level, a Monte Carlo analysis will again consider the same approach, but test the optimization problem considering probability distribution functions of the only influential parameters that were found in this study. Then it is possible to run this sensitivity analysis and determine a set of most promising solutions. So this was the set of P and U in my case study. So we see that we have some material and energy input flows. These material and energy input flows can be converted into methane, into electricity, or hydrogen. To do so, we have several options that we should consider as justification options. We have several options that we may want to include in our plant and which are represented by the industrial utilities. We have, of course, the solar utility, so solar thermal at low temperature, at high temperature, photovoltaics, high efficiency photovoltaics, electrolyzers. So, and then, of course, since the problem is time dependent, I include a set of storage options, such as thermal storage, electricity, batteries, hydrogen storage, and methane. The only thing that was fixed in this problem was the amount of biomass we have here. And based on this, the problem is, okay, what is the path that we have to follow in order to be more profitable, to be more efficient? This problem, there are 53. I more or less try to estimate what are the uncertain parameters of this problem. And I started with 53 uncertain parameters, which are linked with prices, efficiency, and data of the solar radiation we can get. By considering the upper level first step, it was possible to, by computing the minimum total yearly cost, it was possible to reduce and to see only those uncertain parameters that are influential with respect of the model output in this case. And this allowed to reduce the number of uncertain parameters from 53 to 7. So at the end of this first step, the answer of this framework was do not have to consider 53 uncertain parameters because it doesn't pay to have all these sources of uncertainty, but it does need to evaluate the effect of these 7 uncertain parameters. In the second step, so this is a first advantage because in the second step, the number of simulations that have to be run is directly proportional to the number of influential uncertain parameters that we have here. So by reducing by, you see, almost 10 times the number of uncertain parameters, this reduces the successive Monte Carlo simulation. The second step, I applied the Monte Carlo uncertainty. Case, given the probability distribution function of the only 7 uncertain parameters, I run the optimization problem at lower level, and thanks to this, it was possible to collect and rank a set of solutions. So, how I did this? In this case, the idea was every time I test a set of uncertain values on my problem, I will get an answer. So I collect all the answers, and at the end of the analysis, I count how many times this binary solution was the best one. How many times this solution was the best one. And out of this, the total number of simulation, I was able to compute the ranking. So if here we have 5,000 simulations, I rank as first the one that has the majority of solutions. This is the output for the superstructure I have shown you before. So in this case, we see that each of these points corresponds to a selection of utility for a given process. So correspond to a solution of the previous superstructure. In particular, in this case, I organized the plot in such a way that we see that I was considering 5 classification options. And here I highlight which solution have the same classification option. You see that there are some jumps, and there are some difference in total yearly cost and in energy efficiency. And this is driven by optimization and energy integration. These jumps are due to the activation of utilities and to the price of resources that we have set. This, you see that it was, to me, it was impressive that some solutions were optimal with 20% of efficiency. This is due to the fact that in this case, the objective is a single, so the optimization is a single objective, and we have just an economic optimization. So as far as it pays, a 20% efficiency is tolerated. Let's come to the conclusion of this pre-designed phase. By this analysis, it was possible to see that, for example, the most profitable configuration concerning the gasification and gas separation option was the catalytic hydrothermal with CO2 separation, so no hydrogen injection, and a water absorption tower with membrane and pressure recovery. Considering efficiency, even if this was not an objective of the optimization, it came out that if you count, we see that on average, the number of solutions that are most efficient are the one in green. So the catalytic hydrothermal gasification with hydrogen injection, so gas CO2 to be plant output with some recovery and membrane separation for the binary mixture methane and hydrogen was right. Another way to see to display the results. So in this case, we see that for the most profitable path, so for this gasification, this type of gasification, I ranked the 5 best configurations. So I had 22 utilities in my superstructure, and we see that 284 times out of 1,000, this solution was the optimal one. So this is a way to account for uncertainty when we have to select utilities. And it was one of the outcomes concerning to the solar-assisted hydrothermal gasification was that the PV is present, so U19 is present in the best configuration. Concentrating solar trough are present in the second and in the fourth solution, while thermal storage is present in the fifth solution. Considering the most efficient solution, the utilities, the solar utilities were always, I didn't add to the table, but the solar utilities were always present. What are the limitations of this first pre-analysis approach? There is no detailed plant configuration. So this structure I showed you in the previous slide, there is no detailed exchange of heat between. So there is no configuration of the heat exchangers, and there is no optimization on that. And so there is no trade-off between the utilities we have selected, the operating cost, and the capital expense. You can have an estimation, but I will investigate later on this aspect. For this reason, there is a need to go more in detail. The next question was how we can design an industrial power plant and how we can account for multiple periods of operation. So how we can select these utilities, including the heat exchanger network. So the heat exchanger network problem can be defined as follows. We have a set of hot and cold process streams with given time-dependent mass flow rates. We have a set of available utilities, as we had before. We have this time we have some optional heat and energy storage and cost-related data. With this input, we have to determine what is the optimal configuration of the plant. So it is as in the previous step, but a bit more in detail because we have data exchanger network. And in this case, we would try to do this selection by applying a deterministic optimization approach in which we minimize the total yearly cost. As I did at the beginning, I represent here an objective function, so how the mathematical problem will look like in terms of objective function. And one of the main difficulties in this the objective function is not continuous. So you see that there are these points where we have a change in slope of the function. This function is not derivable because we have points in which the derivative does not exist. If we look at the definition of derivative. Jumps, you may ask yourself what is the reason of these jumps, are basically linked to the selection of utilities and with the heat exchanger network. So, and they are linked with the activation of binary variables. So variables that are 0, 1. So given this problem, I consider an existing approach that was a sequential approach developed the year I born, 1987. A sequential approach. So this is the configuration of the heat exchanger network I was talking. And this configuration, sequential approach allows to determine a solution where we have the system is described the heat exchanger. In this case, the decomposition approach is called sequential because we have 3 steps. The decomposition allows to treat large-scale problems, which was one of the goals of my thesis. We have non-isothermal mixing that are basically the point here. So there are possibility of derive some mass flows and mix them in order to save heat exchanger areas. In this case, we increase also the degree of freedom because in a secondary phase, when you have to design a control, for example, you may be able to play with this degree of freedoms in order to satisfy the process needs without the need of changing the configuration. This approach had a low computation time. This is also one of the reasons for which I selected it, but he had 2 main limitations. Apart from the nonlinear constraints that cannot be avoided, the integration of utilities, in this case, using this approach, is possible only in parallel and at the top and at the bottom of the heat exchanger. So you see that this exchanger is different from the other. And this superstructure is valid. So it's considered that this exchanger is in parallel with all the others of this. This is a limitation because the other problem was that this exchanger is placed at very high temperature or at very low temperature. So when we have to describe, for example, a real utility like a gas turbine, for example, this approach does not allow to treat a problem where a gas turbine is included because a gas turbine is a stream that will be present in the middle of between the maximum and the minimum temperature of our system. So based on this analysis, I developed a sequential approach with other authors in which basically I managed to change this limitation and define a superstructure which is able to account for hot and cold utilities across of the real problem. And not only this, but also determine possible series and parallels of in the superstructure of the utility heat exchanger. So then, considering this superstructure, I developed a framework in which I consider a sequential approach. So as I said, we have 3 steps. And again, I applied a B-level approach, where the main idea is to lower level improve the classical sequential approach. So we have 3 problems to solve, 3 mathematical programming models with 3 optimization problems. At first, we have to solve the multi-period energy integration. So this first step equals the step that I described for the pre-design analysis. So we simulate, we solve, and we evaluate. But then, once we have solved we have closed the energy balance, these 2 steps are related to the design of the heat exchanger. In particular, here, the classical approach would say, let's minimize the minimum number of connections between streams, while in this case, we modify by accounting penalty, giving a penalty to each connection and minimizing the total number of penalties. This will give the connection of between hot and cold streams. So this will just give the superstructure that I previously, the basic superstructure that I previously showed. Later on, by applying the third step, which is a nonlinear problem, I determine the optimal At upper level, since these 3 steps are sequential, so we are taking decisions here that may affect the decisions that are taken in the following steps. For this reason, the B-level approach becomes useful because at upper level, it is possible to optimize heat recovery 3 main variables, 3 main group of variables. And these 3 main group of variables will allow to reduce the limitation of this sequentiality. What are these 3 elements? The first element is the heat recovery approach, temperature, which is, for those that are not familiar with this, represents the amount of heat that we can exchange between affecting the heat exchanger area and investment cost of an heat exchanger. Then we can optimize the size of those utilities that I was considering, and we can optimize the penalty level of this step in order to see what are the impacts of considering different heat exchanger configurations to the total cost of the plant. So if we look at more, if we again this part, we have a first problem in which we minimize operating costs subject to 2 type of variables. And we have a minimization of the penalty. This is again function of the heat recovery approach temperature, utility size, and penalty levels. And finally, we have the NLP, nonlinear programming problem, to minimize the total heat exchanger area. Upper level, the particle swarm, the particle generating set complex algorithm proposed by Professor Martelli has been used in order to optimize heat recovery for temperature and utilities that will affect this step, and this. So after having developed this framework, I tested it on a literature case study, and it was by considering the only paper that deals with this sequential synthesis of heat exchanger method. In this case, it was possible to improve just slightly the objective function, which was the total cost. But we see that if you consider the investment cost of the network, these are reduced by more than 13%, and operating costs are slightly increased. Then, since was not satisfied, we decided to test on a large-scale example the 2 methods. So I first apply on a industrial scale case study the classical sequential approach, the one I took as reference. Then, by just including in my approach the optimization of the heat recovery approach temperature, it's possible to improve by 5% the function. By including penalty level, I reached just a slight improvement, but by including the utility, so this was something that here was not highlighted because the number of utilities was very small. While in this case, it was possible to improve by more than 15% the total cost, so the objective function of the problem. Practically, this means that we are able to solve the same problem, but giving a better solution, which means a solution that will be more profitable than the one given by a classical sequential. So this is how it looks like. So we have how the solution looks like. We have, let's imagine that we have 3 periods. So a chemical plant that is run considering 3 periods of operation. We have 1 and 2 hot streams that can be cooled down. And we have 1, 2 cold streams, hot streams, cold streams that have to be heated up. The hot utility and the cold utility. So see that there are some blues lines that are the cold lines of the network that are active at this period. The red lines are the red lines of the network that are active at this period. And the gray lines are those lines of the network that are not active at this period, but in the next period they will be activated. So what the gain for the third period? So we see that, for example, in the first period we have just cold utility in series. In the second period we have hot utility and cold utility. Note that the heat exchangers are always the same. So this brings the point that we have determined a solution of a problem that was time depending, giving a superstructure that allows to operate the system in all periods. Then here I noticed that the storage options were not still included, so I included storage options. And in this case, the superstructure I showed you before is modified because we include the storage tank option. In this case, I consider storage tanks at fixed temperature, and in this way, it is possible to switch to shift energy that is in excess in some periods to other periods where we have a lack of energy. So this time I was stuck with this literature case study, so I tested again the same problem, but in this case I added the storage availability. And in this case, it was possible to reduce the objective function by almost 40%, thanks to the activation of storage tanks. So the solution that I achieved in this case, it was not achieved in this case because storage was not included. We are charging our storage. We are storing energy during a period in which we have an excess of heat, and then we are providing this heat in a successive period in which the energy we have is not enough to supply to provide our demand. Finally, I noticed that my methods here were very expensive from the computational point of view. A problem with a high number with 20 streams can take up to 4 or 5 hours on a computer. So I asked myself if it was possible to simplify this analysis, and if simplified approach they can help in this phase. So if you consider what I had done, I took out these two, so I erased these 2 steps, and they consider 2 alternative methods that allow to just estimate the cost of the heat exchanger without the need of solving these challenging problems. In this case, we consider a global what we call the composite, hot composite and cold composite curve, which represent basically our system in terms of mass and heat loads involved in the process. The main limitations are that with this hybrid and heat exchanger area and post-targeting approaches, we can just evaluate the heat exchange between areas that are vertical. And it cannot be cross heat exchange between these zones. The other problem is that the heat exchangers are sized considering always parallel configuration, which means always minimum area, but not necessarily minimum cost. So considering, then what I did, I consider six test problems in which I solved the same problem with the estimation approach, using optimization, and the sequential heat exchanger network scheme. Every time I was considering the heat exchanger area cost as element of comparison. In this case, it turned out that in all cases I have tested, the heat exchanger area cost is always estimated with respect of the computationally expensive framework that we have developed. In this case, the problems were independent problems. That in the second phase, I decided to focus on one problem and to see if changing heat recovery approach temperatures and considering the same problem can also affect the objective function of the problem. And the answer is yes. Again, with respect of an heat exchanger network synthesis approach, we are overestimating this time not only from 1 to 20, but from 1 to 30% total cost. What does it mean? This means that on the surface I was previously considering maybe not be followed by this optimization algorithm. Finally, concluding this design approach phase, I noticed that there are three classes of problems that we can tackle. The first one is a problem in which we are minimizing the total cost of the plant, and the total cost is the sum of the operating plus the investment cost linked to the area of the heat exchange. In this case, when these two terms are so when the area investment cost, the red one, and when the operating cost, the blue one, are in the same order of magnitude, you understand that having 30% bend on this red function may affect the minimum point of this red function, which is the point I'm looking for. The same happens when the area investment cost is very big with respect of the operating cost of the plant. So having a 30% gap on this, having 0% gap here, and 0% error here may lead to a wrong conclusion. While in the third case, where the area investment cost is very small with respect to the total cost, the only class of problems in which targeting area approach can be applied. So only for this class of problems we can apply the simplified approach, and because you understand that a variation of this point will not basically affect the real function shape. So the final answer was that you are obliged to use numerical approach. The next question was, okay, but I will complicate a bit more things because normally I cannot. I show you that in the first phase I was minimizing the total cost and was getting efficiency that I didn't like, 20% efficiency, not an efficiency that I want to achieve. So for this reason, I wanted to include multiple objectives in my decision making approach. So In this case, I consider investment cost and efficiency as competing objectives. And I took the sequential approach, the three-step approach we have seen before, and they have modified this time, including the multi-objective optimization approach that was proposed by and developed and proposed. In this case, we can not only minimize or maximize one objective function, but we can consider more than one objective function. And so, additionally, I consider the Cosmos platform. So I took what we have developed in our laboratory. It is a tool that allows to simulate process and utility models. In this way, this time, the upper level optimizer will be the multi-objective optimization algorithm. We are able not only to optimize the same variables I was optimizing before, but also to include the time variables. This represents a scientific novelty because in this way it is possible to determine an energy conversion plant in which we have at the same time optimized the design parameters for process and utilities, the utility selection, the operation scheduling, because we are in multi-time, the thermal storage design, and the heat exchanger network team. This represents a novel multi-objective design approach. In this case, if we go a bit more in detail, so we start always from a superstructure with U that we do not know. We know them, we know how they behave in certain operating conditions, but we do not know how in the big picture this will affect the objective function of our problem. In this case, I consider two objective functions: the maximization of the increase of biomass to fuel efficiency when we do not optimize these variables and when we optimize these variables. And I took as the investment cost the second objective. So what happens here is that we start by considering these objectives. We have to give some bounds of these variables, and then we will solve the process and utility models. For the solar utilities, we have the advantage that we know a priori what are the part load performance utilities, because they are mainly dependent on the radiation data we have and on the position of the sun. So we are able to compute the part load performance before running the optimization algorithm. And this is an advantage because it allows to take into account this step staying linear. The third case, and then considering this sequential approach, we solve the heat exchanger network. Finally, given this approach, I applied the framework of for the multi-objective optimization of energy system for the solar-assisted hydrothermal. The goal was to see what are the most promising paths in terms of utilities and if solar-assisted hydrothermal is a viable option. So I consider this superstructure the flow sheet that is describing the catalytic hydrothermal gasification and the gas separation. Then I consider a set of solar utilities and, of course, conventional utilities. So we may use in a gas turbine or in a barn. So we start by setting the location, by setting the only input in terms of size, which is the amount of biomass that it has to be processed in this energy conversion plant, and then find the optimization variable that in this case were the size of the concentrating solar trough, the size of the gas turbine and the burner, the pressure of the catalytic hydrothermal gasification, the temperatures of the salt separation unit, the heat recovery approach temperatures of this gasification process, the temperature of heat transfer fluid of the solar trough, and the heat recovery approach temperature of the solar trough. I wanted to minimize the total investment cost, which is the sum of a set of nonlinear cost contributions. We have the concentrating solar power, the power plant, concentrating solar trough, the storage, some utilities for which the area cost is not representative of the utility cost, and the area cost. Then I wanted, as I was saying before, to maximize the increment of efficiency in terms of biomass to fuel efficiency when we do not have optimization, when we have optimization. So if we look at the solution I got from this problem is this set of points. Again, as before, each point represents this time not only an energy conversion path, but represents operation scheduling of our plant. And for each point, we have the heat exchanger network configuration. So we have at the same time optimized the parameters of design of the utilities, we have sized the utilities and performed the heat exchanger network. What was the major so then considering why we have this shape? So there is a first part of this curve in which the optimization variable that revealed to be the most important was the heat recovery approach temperature of the gasifier. And you see that as far as we reduce this amount, we are able to increase the efficiency of the plant because, of course, we are exchanging the heat in a better way. But to do so, we have to invest in heat exchanger area. Look, the same part of this graph, we see that in this first part of the Pareto front, there is no solar utility integrated. So this is a single period problem. Then, by increasing the investment, the efficiency can be increased, but we have to add finally a trough receiver. The size of the trough receiver ranges from 0 to 2, but you see that after almost 0.9 megawatt, it's not megawatt peak. It's not really paying. So in this case, the pressure and the temperature, other optimization variable were not affecting this approach. The thermal solar utility was between 0 and 2 megawatts. We should, using this approach, if possible, so to increase from 54% to 66% the syngas output. Considering the investment, the ranges are between $500 and $2 million per megawatt of input biomass, and between $1 and $3.5 million per megawatt of synthetic natural gas. Then I add a second optimization scenario in which this time we have the storage added and the PV. So I did the same solution. I fixed the problem the same way. I defined this time I added the variables that are linked to the storage design. So volume, the diameter, temperature of the storages, of the two main storage tanks, transfer fluid temperature of the concentrating solar trough, and heat recovery approach temperature of the concentrating solar trough. Again, the objective functions are the same of the previous slide. In this case, we got this. I got this second Pareto curve, which is shaded in green, and I got the same conclusion. So the conclusion is that we do not have to integrate immediately the solar utilities. We have first to optimize the design of the heat exchanger network, because this can increase up to 4% the efficiency of the plant. After this first action to improve the efficiency of gasification plant, we need to include. We can include the solar utility, and in particular the trough receiver, in order to increase the efficiency. From this time, we do not stop at 12% increase, but we can go up to 16%. In this case, there is a third zone in which we have an impact of the storage. So the impact of the storage is that it will reduce the size of the concentrating solar trough. And this is mainly due to the fact that by storing energy, we can reduce this size. Because we will save energy during the high radiation period, and then we will be able to deliver this heat to the process. Concerning the PV integration, since the gasifier does not have a very big electricity requirement, we are below 50 kilowatts. Let's say we are below 100. Yes, we are below 50 kilowatts. The size of the PV is not affecting the optimization because the added cost of this technology is very small compared to the added cost of the storage and the concentrating solar trough. As before, some other optimization variables were not important. In this case, the solar trough is between 0 and 1 megawatt peak, and we have increased the efficiency up to 16%. So the benefits of the storage are that you can even push the efficiency of the plant out up to 16%. In this case, it was possible to convert starting from 1 megawatt of biomass. It was possible to convert up to 540 kilowatt to 700 kilowatt of synthetic natural gas with an investment that this time in the same order of magnitude. For some solution, it's even lower because we save cost for what concerns the trough receiver, and because the cost of the storage is not so impacting as it is for the thermal power. So if we look then at each point, we see that this part of the Pareto, so up to 4%, each solution is a single period because there is no solar utility. So it's even a easier problem to solve. We have a fixed gasification demand in heat. We have a fixed fuel that need to be burned in order to supply this heat. But so we didn't solve the starting problem, but we were able, in any case, to improve Then, for this last point, we have a system which is behaving in multi-period. And in this case, it's possible to convert 1 megawatt, which is delivered by the trough receiver, into a 1 megawatt dot 16 of synthetic natural gas. Why this is possible? This is mainly this is related to the exergy of this heat, so to the temperature level at which this heat is available. The gasification heat demand is at this temperature. Normally, you have to burn this amount of synthetic natural gas, and we have a part of heat which is waste. By including the solar heat at high temperature, it is possible. So for 1 megawatt, which is delivered at this temperature, we do not only save this megawatt that was the useful effect when we were burning SNG, but we always save this waste heat. And again, for each of these points, we have the heat exchanger network configuration, which is something that was not shown in literature up to now. Coming to the conclusion. So in my thesis, we have defined this method that allows to identify energy conversion paths. It allows to account for uncertainty of linear and non-linear parameters. We can use it to account energy integration principles and investigate what are the most promising technologies. Out of this, the application of this method to the catalytic hydrothermal gasification with solar utilities, including the superstructure, it was possible to see that catalytic hydrothermal with water absorption and concentrating solar trough is a promising energy conversion path. The outcomes, then some other outcomes are that the energy integration is the driving force in this section. Numerical optimization is often driven by assumptions, so it is necessary to account for these uncertain parameters. And with this framework, it is possible to explore the search space and to identify the bottlenecks of a given problem. It would be nice to have the same analysis for the same infrastructure considering different objectives in order to have a more detailed view of the problem. And it would be also useful to extend the framework to the optimization of design parameters, including heat exchanger network. The second, in order to answer the second research question, I developed this framework, so it's possible. It's a general formulation, so it can be applied to any industrial plant design that can be represented in quasi-steady state operation. It is possible to treat industrial problems, so problems with high number of streams, with a reduced computational effort, if we consider a single sequential approach, and including also multiple objective optimization. In this case, it was possible to optimally select the utility, design it, and scheduling the utilities, and including the heat exchanger network. And concerning the numerical optimization methods I have analyzed, the conclusion is that the method to be selected is really dependent on the problem we have. It would be nice to extend even on a larger scale this method and to compare this approach with simultaneous design and control. Finally, concerning the hydrothermal gasification, we have proposed a set of solutions, a plant designs in which heat exchanger network is provided. Solar-assisted catalytic hydrothermal gasification may be viable. I stopped my analysis to the investment cost, so as these results can be used to compute the operating cost and to evaluate the plant profitability for different economic situations. We have seen that using this approach and considering the technologies I have added to the structure, it was possible to increase the methane conversion from waste biomass up to 15%. And it is also possible to convert 1 megawatt of high temperature heat into 1.16 megawatts of synthetic natural gas. But unfortunately, the investment costs are increased by almost 4 times. So, as for all renewable energy. It would be nice to include uncertainty inside this heat exchanger network design framework, but this would increase the computational effort. And it would be also nice to extend this analysis to multiple scenarios. I start with the acknowledgement.